So I did say the end goal was calculating transfer of heat. So that is if you have object A, perhaps touching object B somehow. Okay, and if that red was hot and this was cold, then heat would travel this direction based on our second law of thermodynamics. You can calculate how much heat is transferred, okay, in that, or you can calculate what the final temperature of both will be, or you can calculate various things. But transfer of heat can be done in three ways, okay, by conduction, which is basically this, okay. When we talk about collisions, transfer of heat will depend on collisions. If you have a big surface area, then you're going to have a very big transfer of heat. The thickness of a material will slow down the transfer of heat. More temperature will increase it. But it comes down to collisions. So this one's moving a lot right here, lots of collisions, and those collisions will basically force these particles in this object to move around much quicker as well, and eventually everything will be vibrating. You can kind of think about like vibration. Convection will be so by the way, this is conduction, not radiation. That's what it looks like, isn't it? This is conduction. Convection will be the movement of molecules from one place to another. So you can buy convection ovens where you where it will essentially begin through conduction. You have elements at the bottom or at the top that will heat up, and they will heat up the air and create a current, which will heat things up via convection. Radiation is kind of the last one, which is basically energy transferred through space in the form of electromagnetic waves, okay, through light, essentially. So that is how our planet is powered, solar radiation. Okay, that's how we get our energy. That's how we get everything, actually. So that's the sun and earth. Energy transfer, which is great. So you can watch a little video about conduction and convection. You can read about radiation if you wish, but let's get down to some of the useful experiments that we could do with this. So calorimetry is how we will measure heat transfer. If one object loses heat, the other gains heat. There, that is the second law of thermodynamics, and it can be summarized by this lovely formula. Now, in another video, okay, I'm not sure if I'll do this yet, but I think I will, perhaps later on, I will show you how to derive this formula, okay? It's derived from Q equals mc delta T. Okay, how do you see that? Well, you can see that clearly here and clearly here. Basically, if you have two objects that are touching, each of them will have their own mass. If this is A and this is B, they'll have their own mass, their own specific heat capacity, their own initial temperature. That's what TAI means. And then B, of course, will have its own mass, its own temperature, its own specific heat capacity, and its own temperature. Okay. Now, how do you actually derive that to be the final one? Let's do that in another time. This video, let's focus on computation, which is probably something that people are more interested in when they first are introduced to this, and then later on you can come back and look about how you actually get this, which is kind of counterintuitive in learning, but sometimes I think people like to get their grasp on the computations first. You can rearrange this formula, and certainly you might have to individually rearrange them, but I've taken the liberty to rearrange you two common ones, which is if we want to solve for the initial temperature of one of the objects, or if we want to solve for the specific heat capacity of one of the objects. This one we'll use in a lab. Okay? Because we're going to use this in a lab to determine the type of object. So, I think, yeah, perfect. This is outlining what you can do. What's the point of this? Okay, this is a calorimeter. This is how you can measure changes in thermal energy. Basically, you have two substances touching each other. Okay, In this case, the one substance is typically water. Okay, that's this right here. What you do is, let's say you have some unknown substance that's sitting on this stick. Now this is one of the applications, but this is the one that we'll do. You don't know what this material is. It's going to be some kind of metal, okay? But you do know its mass, and you do know its initial temperature. You'll measure its initial temperature. You also will know the initial temperature of water. Okay, so you'll have all these things. So you'll have that, T water, the initial, you have the mass of water. You'll also have the specific heat capacity for water. This thing you'll know the mass, let's call it B. You'll know the temperature of it. But what you won't know, whoa, can't spell no. Oh, for crying out loud. You won't know the specific heat capacity for this substance. Because if you know the specific heat capacity, that means you know what the substance is. So that's what you don't know. But the question is, how do you figure that out? Well, you need one more piece of information, right? Look back in the formula. I just gave you this, not this, right? They repeat. And I haven't told you this yet. But that's the whole point of the experiment. What you do is basically, you have a thermometer here. These things are different temperatures, probably. Okay, the water's at some, room temperature, 20 degrees Celsius. The material can be, I don't know, at 15 degrees Celsius. You put them inside, and eventually, over time, what will happen? They will reach thermal equilibrium. And that's basically TF. So your final temperature is when they reach equilibrium. That's when all the energy that's possible has been transferred from one object to another. Okay. By the way, if you start with the same temperature, that's profoundly useless because nothing will happen. So you want them to be vastly different in temperature. Let's say the water's at 20 degrees Celsius, the rock's at some large amount, 100 degrees Celsius. Therefore, you know the initial temperature of the material. You place them in, and boom, you will figure out what the final temperature is, which means you'll know all you need to know to solve for that guy. And then there is much rejoicing. Once you get the specific heat capacity, you can look up on a table what material it is. So that is how you can find to identify what a material is. So this could be iron or steel, depending on this value. So let's do some computations. This can get ugly, but I'm not going to make it ugly, actually. In this, it looks ugly because I included the units. Because you really should include the units, and from my perspective, I'm showing you how to do this. You can see how the units will cancel and give you Celsius. Oh, I was going to sneeze. But when I do this in the next example, I'll omit some units. So, here we go. I'm assuming you've read through this one right here. It looks big, but it's really not that bad. A 0.5 kilogram sample of water is at 15 degrees Celsius. A 0.04 kilogram block of zinc is placed in the water. If the final temperature of the water is 15.73 degrees Celsius, determine the original temperature of the piece of zinc. Okay, so for the sake of this example, we'll let water, I would do this if I were you as well, equal W, zinc equals Z. Okay? Therefore, the formula, and what are we looking for? We're looking for original temperature. Okay? So when you go back, out of these three arrangements, which one is it? This guy, because this is initial temperature. That's your initial temperature formula. In this case, we're looking for the initial temperature of zinc, right? Z, which means it's going to be TZI. Whoa, wrong way. Whoa, come on now. Thank you. It means it's ridiculous. There we go. TZI is equal to, I believe, you're replacing Z's with A. You're replacing the A's with Z's now. So it's MZ. Oh, why did I put that comma? Sorry. Oh, and I'm just messing up here. This is what we got to copy down. Okay, TF, MA, CA. We're replacing all the A's of Z's and all the B's of W's, basically. So, perhaps I'll pause the video and I'll just do this here. So, the magic of editing has allowed me to get that down. So basically you replaced all the A's with Z's and all the B's with W. That's because you're looking for the original temperature of zinc. So what do you actually know? Well, you know TF. The final temperature, it tells you, it's this. 15.73. It does say the final temperature of water, but of course thermal equilibrium necessitates that is the final temperature of the zinc as well. The mass of zinc is 0.0400, 3 significant figures. And then the mass of water is 0.500. And the initial temperature of water is 15 degrees Celsius. What else do we gotta know here? Specific heat capacities. We gotta get those bad boys. So this is, for water, I think it's 4180 joules per kilogram times degrees Celsius. For zinc, I do not know. Gotta look that up. Let's see if my water one was right. Yes, it was. Zinc 388. So you're referencing that. 388 joules per kilogram degrees Celsius. So when it's not given to you, you're gonna have to reference it. There they all are. There's all the 7 variables you need. So now you can plug them in. Now I'm gonna make it easier. I'm gonna change colors. That's not what makes it easier. What's gonna make it easier is, sorry, I'm just uploading videos here, is I am going to omit the units so I don't run out of room. Hopefully I can do this in 2 minutes and 30 seconds. Here we go. TF 15.73. So yes, I am plugging this in. 0.04. I'll just forget about those two other things. Times, whoa, gotta make a bracket here. Times 388. We're gonna run out of room. This is not good. This is not good at all. Oh boy. A tragedy. Times 0.5 times 4180. Yeah, definitely ran out of room. I'm just gonna put this one underneath. The initial temperature of water is 15 degrees Celsius. This is all over MZ, which is 0.04 times CZ, which is 388. Okay, well, how would you compute this? You can actually compute this in one step if you're familiar with the store and recall button in your calculator, or if you're just really confident with brackets. However, most people like to compute in chunks. So most people like to compute this first. Write that number down. Don't round it. This second. And then this third. Then they add 1 and 2 and divide that by 3. So 15.73 times 0.04 times 388. When you compute this guy out, here's what you get. Well, the numerator, typically I like to do this all in one step, but let me just split it up so you guys get some checkpoints. So that is the addition of 1 and 2. That's the whole numerator. The denominator, and I actually stored that. You might have a button in your calculator that says store, and I stored in a variable called x, which is not necessary, but it is handy. So here I'm just going to recall the first one, divided by 15.52, and let's see what we get. We get 114. We are to, let's see, 3 significant figures here. 114. degrees Celsius was the initial temperature of zinc. And that's it. That's what you have it. Unfortunately, I exceeded the 15-minute mark. Sorry about that. So I would suggest you copy down these 3 variations of the formula. You just have to go very slowly. You know, you plug and play, and you're going to get an answer. And it's no more difficult than the other ones. But you just have to be careful. So work on those practice problems, and then finally move on to the next section.